Okay, so I was a little challenged because Nathan asked me not to be too salesy. So what it meant was that I pulled out stuff from a number of presentations, and let's see how smoothly it goes. What I'm going to focus on is the technology, and it was very similar to a presentation that I did a few months ago in Montreal, talking about how to improve internal rates of return on greenfield projects by using instrumentation and control. On average, instrumentation and control will be between 1% and 2% of the total project cost. But just from an optimization standpoint, that's going to give you 5 to 10% increase in throughput and greater than 2% increase in recovery, let alone what it does at the base level. Instrumentation and control have been huge hurdles for many greenfield operations that have started up just recently. A good example is Pueblo Viejo, which had a ton of trouble on that side. Right now, we have two guys at Boleo. If you're familiar with Boleo mining in Baja California, where they're having some real challenges getting their instrumentation and control off the ground. And we were just recently down in Argentina at Cerro Negro, who likewise had a target for startup, a 5-day target, and we came down and it was clear that with their I/O and all the other technology, it was going to be weeks away. Often instrumentation control is pushed down to the bottom of the heap. We focus on our major pieces of equipment first, but it can very often be the speed bump or the hurdle that prevents us from starting up when we want to start up, and certainly prevents us from achieving what can be achieved with the equity and the assets that we've invested in. I'll quickly just mention who we are. So we're focused on operations optimization. Our head office is here in Toronto. We have operations in Canada, Mexico, and Chile, and we're opening Australia and South Africa by Q2 of this year. Okay, so when we say operations optimization, our focus is how can you do more with the assets that you have installed? And I'll explain that as we go through. So what are the challenges that I see time after time going to different sites around the world? Variable ore types, they're all variable. Everybody talks about how their ore type is more variable than everybody else's, and I'll show you some examples. But we have to deal with that, and we have to handle that as far as operations go. Complex processes. Our industry is misunderstood, I believe, by other industries. People in oil and gas think they're a lot more complicated than us because of all the thermodynamics that they're using to model their processes. It's just the simplicity of our processes that make it very difficult to operate. I'll talk a bit about that. Fewer experienced operators. I'm sure everybody that's in operations in this room is experiencing the struggles that we all have with finding people that know what they're doing in the plant. The competitive market, which you mentioned just earlier, and dispersed operations. One of the things that people complain about, or to me about all the time, and this is happening right now at Boleo, is that they don't feel they get the love from the large organizations. So the Siemens, the ABBs, the Emersons of the world. They put a ton of energy and give a ton of love to oil and gas. Why? Because they can really focus on it. It gives them a lot of revenue in a very small geographic area. The problem with us is, if you look at Barrick, Barrick is a great company, with some fantastic operations, some great opportunity for these other companies to capitalize on their technology, but they're spread around the world. So they're in different geographic regions, and in any one of those geographic regions, they don't necessarily make up enough of the revenue to capture the attention of the local group. And so as a result of that, we're often somewhat neglected by these larger companies, unless you're dealing with a large company that's focused on minerals, such as a Metso or an Autotech or something like that. And so when we talk about variable ore types, some people will recognize some of these graphs. These graphs are all looking simply at hardness. So however consistent we believe our ore types are, there's huge variability as you move through the ore body. This is a single bench from Escondida, the world's largest copper mine. I think they're now at 350,000 tons per day, and they're going to 500,000 tons per day. They've already started the design or the engineering on that, and their goal is to reach 1 million tons a day. So incredible scale. What the different colors are showing you is hardness variability across this bench. Each of these are showing hardness. Here is a 300 by 800 meter section. Hardness is on the y-axis. So it's this variability that's hitting our plants continuously. And part of the challenge with our variability is we don't have a homogenization step. So unlike oil and gas, where everything comes together and becomes one feed, or unlike pulp and paper, where once we break those lignins, in the digester, we become one feed. With us, it doesn't matter how fine we grind our material, each particle is individual. And it's that variability that we're dealing with. This is actually from the Yukon. I'm going to show you another one. This is from Wolverine, Yukon Zinc. And this is their copper grade. These are half-hour increments. And you can see that it goes from 0.7 to 1.5 in half an hour. Their operators have to respond to that. Their operators have to change their reagents. They have to change the way they're running their float circuits due to that variability. This is a flow sheet for a project we're working on now in British Columbia, a molybdenum project, Avanti, if you're familiar with that, kit salt. Again, our unit operations as individual unit operations seem very simple. Big drums that are rotating and crushing ore, flotation, bubbling air through, and we're coming out. For an operator that's running this, there's a lot that he has to consider. He has to consider the feed size to his sag mill. He has to consider the transfer size between the sag and the ball mill, and ultimately his product size, right? It's all about liberation. That's why we have our grinding circuits. He then also has to manage his circulating loads within that grinding circuit. Now, when he gets to the flotation circuit, this guy has to run 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 circulating loads he has to manage around that float circuit. So he's trying to achieve optimum performance from this float circuit while managing all of this. And I'll show you in a bit. There's typically one operator in that control room that's doing this. People. So Chile, 15,000 engineers in the next 5 years for $100 billion in projects. That keeps getting pushed off a little bit. You talked about governments and the challenges environmentally in particular, and there we can point out Pascualama, not Cerro Negro, El Moro, Quebrada Blanca Dos. They've all been postponed due to environmental uncertainty. Peñoles is building 7 plants in the next 5 years. They're hiring 50 engineers a month and training them in-house to get them ready for their plant startups. This year, for example, they did Herradura and Saucito Dos. San Julian is next year. Even in North America, the average age of our operator is over 50. They say that half of our workforce is going to be lost in the next 5 to 10 years. So not only is it training people and bringing them up to speed, what we're losing is a lot of intellectual understanding of how our processes work. When I started in the industry, the operators would be able to grab their froth, they'd touch it, they'd taste it, they'd throw it in the air, and they'd be able to tell you what the grade of that froth was. We would walk on the floor, back in the day up in Marathon, we'd walk on the floor and we'd listen to the sag mill, and based on how the sag mill sounded, we would make modifications to that mill. That expertise, that experience is lost. And that's why we need to start looking more at training and looking more at instrumentation and control to help them, provide them with tools. So how do we deal with the challenges? I'm not going to go into these in details. I'm sure you'll have other people come in and talk to you about various different technologies. But I want to show it's not just instrumentation and control. There are other things. So one of the things that we're looking at for the variability is geometallurgy. One thing that we look at as far as the complexity of the circuits and that variability as well is different technologies, and I'll mention a couple of them. And finally, we get into how do we actually control that plant and run it. So geometallurgy, for those of you that aren't as familiar with it, is the whole concept of designing with variability quantified. Understanding what a representative profile is throughout your circuit as opposed to a representative sample. And more companies are doing this, where we're actually able to apply statistics to metallurgical principles as well as principles such as metal content. Okay, so with this, we can better design our plants. We can understand and quantify our risk, and we have the ability to design temporally, so we don't have to put in a crusher today that we might not need until later. From a technology standpoint, there's new technologies coming out all the time. My Old partners have this new flotation reactor system called the SFR that some people here will have heard of, and I know they're working with a few of the companies here, which allows for better responsiveness to variability within the ore and substantially less power consumption. The HPGR is another good example of a technology that can absorb that variability and in certain situations makes sense depending on the hardness. The theme here is that we're able to now design and we're continuing to push our technology to the point where we're getting our major pieces of equipment more robust to this variability. I find it interesting that I'm seeing a step away a little bit from SAG mills. Goldcorp just started up Eleanor, 3-stage crushing grinding. Right? There are a number of projects around the world when I speak to them that are looking at 3-stage crushing grinding. Their main reason for that is because of the people issue. It's a much easier circuit to operate and it's more robust to variability in hardness. So it shows how we're responding as an industry to the challenges. So we can design considering that variability. We can install more robust and cost-effective equipment. So now we know how it can handle the ore, but we have to figure out how are we going to manage this process? How are we going to run the plant? I enjoy these next two slides. I think they're very appropriate. Operators in our plants are often compared to commercial pilots, right? They're both responsible for the safe operation with potentially huge ramifications for mistakes. They rely on engineers, unfortunately, for robust, reliable design. And they rely on maintenance personnel to keep their equipment running. They're just sitting behind the seat, keeping this thing flying. They're both the last line of defense, right, for any problems. So how similar is the cockpit to the operator console? A commercial airplane pilot can have over 100 controls that he's managing at any one time. The operator in a typical mineral processing plant has over 300 controls that he's managing and monitoring. So the joke is that it's as if he's flying 3 planes simultaneously. But the real joke here is that the pilot has fantastic instrumentation. His instrumentation tells him everything that's happening inside and outside of that plane. Our operators are operating with one eye covered and the other one blurry because our instrumentation just isn't developed to that extent. So this guy sitting in the control room is trying to manage that plant. So what does he typically do? He has to step back a little bit from where he could push the process. Give himself some room for error because he knows that his attention is going to have to be divided. Again, this is what he sees. This is that Yukon zinc again, but this is on a 10-minute basis. So you see here it goes from 0.6 to 1 to 1.2% copper, back down to 0.6. 10 minutes. And this guy's trying to run that circuit. This is from a mine in Quebec. This is the set point that they have for the tonnage, and this is the actual present value of the tonnage feeding that mine. They're mine limited. So what that means is they don't have a healthy stockpile, so they're not able to feed it consistently. Again, that sort of variability, this is a 24-hour period, the operator's having to respond to that. So when we talk about control and optimization in particular, our objective is to first take that variability away, stabilize the process, and then once you have a stabilized process, allow ourselves to move closer to the constraint of our equipment. And that's everything that we're focused on. And these are some results of the of what you can get in the plant by using better control. This is from a plant up in Timmins. This is the level in a flotation cell. The red that you can barely see is the set point. The blue is the actual level. Before and after applying advanced control. This is a flotation column, before and after. This is rougher feed density, which is essentially the overflow from your cyclones, an 80% reduction in variability. When we're talking about cyclones, their principal job is to give you your liberation, right? To give you your cut size. When you're getting variability like that, the liberation on your mineral is moving all over. Your particle size is moving all over. An 80% reduction means that everything downstream is going to be that much more stable. And you're going to be able to then push your process closer to its limit. Here are just some examples from some plants around the world where we look at again, the real opportunity. So this period here is about an hour and a half. And what we can see up here, this is a SAG mill. So we're looking at the pressure and power of the mill, and it indicates how the mill is performing. And here we're looking at the tonnage. So I'd really like to focus on the tonnage. This particular mine is in Peru. What we can see is for an hour and a half, they're at significantly reduced tons. Here, all of those places, the operator had to make massive corrections. With process control, what we're able to do is truncate those corrections. That's where the benefit comes from. This is the example from BC that I was mentioning earlier. They were able to get a 1.3% increase in recovery, a 6.2% increase in throughput, with a payback or a benefit of $16 million a year from putting in better control after they had started up. This is a plant in Australia. And again, the red is the tonnage. Look at that variability, right? That's noon till midnight. Correcting that variability will add revenue between $22 and $49 million to this particular operation. Significant opportunity. And it's not only opportunity with respect to throughput and with respect to recovery, there's opportunity with respect to power. So this is a mine in Mexico, and you can see there was an increase in throughput, but what's really interesting was the reduction in kilowatt hours per ton of power. This is a mine in Canada, 6% reduction in kilowatt hours per pound of copper produced. Now what's interesting is more and more governments are starting to sponsor these sort of programs. So British Columbia has a great program where it looks like they're going to be paying for 2 of our systems to go in at different mines there. They will pay if you make your mine more efficient from an energy perspective. And this is going to happen everywhere. I mean, when you look at Chile and the cost of energy in Chile, it's something we all have to be cognizant of. Okay. So how do we capitalize on the opportunity? First, what we need to do within the control sphere is we have to recognize that each site and each mineral is unique. Even though they might all be copper, copper is not copper, is not copper, gold is not gold, is not gold. We have to recognize that, and we have to keep that in mind when we're designing a solution. Again, one of the challenges that we had with this technology in the past and where people became frustrated with it is we would use cookie cutter designs for control. And the problem with cookie cutter designs is, the problem with the average is there's very few plants that are actually at the average. They're at one of the 2 ends, which makes the average. You create a site best operating practice, and then you take that site best operating practice and you close the loop and you implement that in a real-time basis. Typically using technologies such as model predictive control, multivariable control, but also using artificial intelligence. And today in the world, there are close to 400 plants that are being run with artificial intelligence-based solutions, AI. It's key to recognize, though, that we can only manage what's measured and we can only optimize what's controlled. Really important, including for our operator that's sitting there in the control room. If he can't see what's going on, if he doesn't have an understanding of what's happening in his circuit, he can't manage it. So he can't be running blind. When we look at any sort of solution, there are always 3 components. The most important contributor is the data, right? Garbage in, garbage out. You can only manage what is measured. You have to have that measurement. People often focus on technology next, but in actual fact, technology, I would put third, because technology in and of itself does not give you a solution. I make the point that we all have Excel on our machines. Few of us use more than 10% of the functionality of Excel. So simply because you have a technology available to you, it doesn't mean it's going to be adopted, or it doesn't mean it's going to be effective. So what's most important is how you implement this technology within the culture of your organization. What works in Papua New Guinea won't necessarily work in Chile. And what works in Chile won't necessarily be the right solution for Canada. So when you look at this, what you do is it's called fit for purpose. First, what you do is you understand your process degrees of freedom. What hooks and handles and levers does the operator have that he can move to actually run his plants? Then you say, what do we need to measure in order to manage those degrees of freedom? How do we bring the process under control? And only then do you move to the point of optimization. Within Portage, we have a number of solutions that take us through this. What I'm going to do is focus on some of those measurement solutions that I was mentioning earlier, and how we actually bring it under control. You saw some examples of this already. So one of the things we do is, with flotation is more of an art than a science. People look at the float cell, and based on what the froth looks like, they make changes. If we can change that so that we now have a measurement, it means you're going to have more consistency between your crews. It's a great example of how so much of our data used to be inferred. The way we control flotation cells is we manipulate level and we manipulate air, which impacts our froth. But what we really care about is what's the mass pull coming off the top of our cell. So we are controlling based on a manipulated variable, but our actual control variable is the mass pull and the bubble quality. Cameras give us that. But once again, you have to be creative. These are screens from Papua New Guinea, from that barrack site. They have a major problem, a challenge, let's call it a challenge. These are the launders here. And their challenge is, they're doing a lot better now than this plant was originally designed for. They're producing a lot more froth. So the problem is the froth can't get out of their launders. So they were often flooding their cells. You'd walk, the basement would be covered in froth and concentrate. With the camera systems, what you're able to do is we put a plate in the launder. So here you can see there's an empty launder. The plate's nice and bright. Here you can see the froth is starting to cover the plate. We can recognize that. And by recognizing that the launder is filling, we can change our operational strategy. That makes sense? So it's that flexibility. Then we look at particle size. We spoke earlier about a SAG mill. And the thing with a SAG mill, semi-autogenous grinding, is that grinding occurs both by the steel as well as the material that's in the mill. So the material that you're bringing into the mill is extremely important. It's your grinding media. Up until now, operators would look on a screen and, based on their best judgment, decide whether that grinding material that's feeding their mill was what they needed in there. Now we have the capability of putting cameras on the individual feeders, so we know which feeder's coarse, which feeder's fine, and which feeder's middle. And they're able to blend that in order to get the F80 that they need to operate that plant and adjust it with respect to that. And here you can see it installed in a feeder box. So this is the ore, but we saw it live. So normally this is where I go to those live images. This is an example from a plant up in northern Ontario. And here what we see is we have the power and the pressure in a mill. And what we can see is we've had a major ore change at this point. Normally what you would do is you would cut the tonnage when you have an ore change like that to figure out what's going on and then bring it back up. What we were able to do was adjust the ratio of the feeders in order to keep the tonnage constant and recover the mill. So it shows how you can start using these technologies to squeeze more out of your operation. Another advancement as far as technology goes, as far as reading, one of the issues that we have is these cyclones are run blind right now. We measure pressure, we have a cyclopack. One of the problems that you get with cyclones, a significant problem, is called plugging or roping. Both of these, what happens is that the cyclone stops doing its job. With plugging, you plug the bottom, everything goes out the top. With roping, you lose the capability in the cyclone and you essentially, it becomes a T. So much so that I'm trying to come up with the number. At one of the plants, when they dump their first cell to clean out their first flotation cell, it can be between 30 and 40% filled with coarse. Right? As we look here, typical plugging or roping event sends, in this particular mine, which is 25,000 ton per day property, 15 to 30 cubic meters of coarse to flotation. Their float cells are 200 cubic meter cells. 50% of that will float, but the other 50% is just going to sink. Those cells weren't designed to float coarse. So you're impacting the hydrodynamics of your cell, and you're impacting the residence time of your circuit. We now have technology that can detect on a real-time basis when you have a plugging or roping event. These are two cyclones in the same cycle pack next to each other, and we can identify immediately when we have a roping event, and we can switch it out within 5 seconds. Where this is moving is also looking at the liners. So when you get to the maintenance side of your cyclones, what happens now is people replace liners in their cyclones based on hours of operation. Typically, well, many plants is 3,000 to 3,500 hours of operation. By using the same device, we can actually measure and monitor the wear. So if we can get another month or 2 months of operation out of that liner, which makes a lot of sense, then of course that's money. At the same time, there are many operations where well before the 3,500 hours, you've worn through the rubber because you've had particularly coarse and abrasive ore, and now you start wearing through the cyclone itself, right? So it just shows you how we use these technologies. Doing the same thing now on SAG mills. So putting vibration sensors directly on the mills to measure the vibration, measure the performance of this mill. To give you an example of the benefit of that, with vibration, you're able to detect the loading or unloading of the mill up to a minute or minute and a half before you see it in the bearing pressure. If you're getting advance notice that something is happening, obviously you can respond that much more aggressively. And by responding that much more aggressively and that much more preemptively, you're going to get the benefit in your throughput. The next phase, where R&D is going on right now, is putting these same sensors on flotation cells to understand once again from a vibration perspective how that flotation cell is working. This is taking technology that was very common in machine health management, so shovels, and where they can measure 1/8 of an inch of wear on a bearing and taking it into process. And that's a big part of what you see in our industry in particular, is people leveraging what we've learned in other industries, whether it's in space or in medicine, and applying it to our industry. One more example of using vision technology. This is Radomiro Tomic, the largest copper cathode plant in the world. It's a Codelco property. They produce 900 tons per day of copper. What they do now for their cathodes is they have an individual that's watching those cathodes come out. He has 1 to 2 seconds as it moves in front of him and it stops, and he pushes a button of whether he's going to classify it as grade A or grade B. This is a guy that watches and makes that decision. If he's been out drinking or celebrating the Leaf win over Dallas the night before, you know, he might have trouble classifying that. 50% are incorrectly classified. We have the ability with vision technology to classify it automatically. 50% of theirs are incorrectly classified. Almost done. Yeah. So now we've seen the measurement side of how we can measure things to manage it. And now we move into then how do you control and optimize. And as I mentioned before, there are many different technologies out there to do that. But the one that I think is most interesting is the whole concept of the artificial intelligence. Because still within our plants, we cannot model things as well as we would like. We're getting better. And you're seeing more and more model predictive and multivariable control. Those stability slides I showed you before are all using fundamental models, mathematics, to help us stabilize the circuit. But when it comes to optimization, it's the big picture that we have to consider. And there we're using artificial intelligence, fuzzy logic neural networks. But one of the important things is that as you progress with respect to technology like that, you have to make sure that you give information back to the plant so that they can manage that technology. And that's what I mentioned earlier, this whole idea of the people and how the people fit in. So because we're using those more advanced technologies, we now have the ability to monitor how our control loops and how our instruments are working. For example here, 100% of this day, this particular weightometer was maxed out. This control loop for a weightometer was maxed out. 85% of the day, or is that 75? 75% of the day, this flow meter was at its minimum. It was as shut as it would go, and it couldn't go any further. So that's directly impacting your operation. Because of the time, I'll skip this slide. And here we're able to see, for example, where our throughput was constrained through the day. So if it's a ball mill pump box that's preventing us from putting more throughput in, we should consider replacing that pump box, right? 15% of the day. So my final 2 slides are on the next stage, because we're speaking about people. So now we've said we're giving them better tools, but we spoke earlier about the experience and the learning. One of the things that's being well adopted within our industry is this concept of operator training simulation. An operator sits in a room. It's just like the control room he's going to sit in the plant. The only difference is there isn't the noise, there isn't the vibration, there isn't the dust. And he's able to use the same control system that he'll be using in the plant that will respond in the same way that the plant responds. These are two interesting graphs. When we look at industry production losses, this is from ORADA failure data from, I believe it's 2012. Operator error, almost 90% of the contribution to loss. I found the sabotage arson to be an interesting one. And when we look at how we learn better by doing than by anything else, other than teaching. But so often we're training our operators in rooms. One of the things that we're looking at doing, and we're with the University of Chile, we're starting up a center down in Chile. You need a license to do almost anything. You need a license if you want to work in the plants and work in the electrical side of the plant, you need your ticket, right? You need a license to drive your car. The guys that drive our sag mills and the guys that drive our crushers and drive our float plants don't need any experience. They learn on the job. So why not train them to a minimal level so they understand the basics before they enter the plant? And that's what we're looking at using the operator training for, as I said, with the university down in Chile. That's
Thank you so much.
about it.
Thank you, everybody.
There you go.